Alright guys, so we're looking at circular motion this morning, and you've probably already seen the video I posted some time ago. I want to quickly run through the basics before we start with some problems. So obviously we have something in a circle. I'll pick a different pen. And it's rotating, maybe a conch on a string, something like that. And if we start off the motion here, and a little bit time later, it's gone through this arc. So we've got a delta t, and in that time it strikes at an angle. So we have got something called an angular speed, which is referred to as omega, and that is the amount of angles struck out per second. So that seems fairly clear. There's another way of looking at this, and you can just think of looking at this arc here as a distance. So we will be looking at a speed of distance, so that arc length of x over time. So let's put deltas in it. That distance could be found by measuring it, or if we make the problem even simpler and think it transcribes an entire circle, then that's simply the circumference, and that would be over the total time, which would be the period time. So the time for one complete revolution of an object in a circle is the period time, and that's given the symbol capital T. Now we all know the equation for the circumference of a circle, 2 pi r, that's the radius of my circle, over t. We might also remember that t is equal to 1 over the frequency. So this implies that we can write this equation here for my velocity as 2 pi f r. So that's an equation for velocity, and that's an equation for velocity. But we want angular velocity. So we could do that because 2 pi over t and delta theta over delta t, well, that's very similar. We're going to just define 2 pi, if I can spell 2, as being equal to omega. Now, can you see therefore that the angular velocity can now be given this symbol, velocity, equals omega times r. So there's my omega term, there's r, and I've got another equation for velocity. So this is a key equation, velocity equals omega r. Now we measure omega in a unit called the radian. So omega is in radians, and you probably realise this already from maths, that you've got 2 pi radians in 360 degrees. Or pi radians in 180 degrees. So you can work out what 1 rad is by dividing by 180 by pi. Okay, and that would obviously be in degrees. So 1 radian is equal to 57.3 degrees. So that's interesting. But if we keep it in 2 pi over t terminology, then we're just measuring the angle in radians, and it doesn't make any difference. So don't bother to convert to degrees unless you're asked to. What else can we do? Oh yeah. So up here, I just pick a different colour then. If I go back to this diagram and we look at the velocity of the point of this whirling object here, you might see that it's going to be a tangent to the curve at that point. Later on, it's now moved to here. It's now a different tangent. So this is my initial velocity, this is my final velocity. And we know that acceleration is a change in velocity over a change in time. So if we look at this vectorially, then we have the final velocity here. So v minus u over delta t gives me acceleration. So that's my v. And then I want to minus u from it. So minus u well, it's not quite right, but you can see where this is going. And then can you see that I've got a change in velocity in that direction, which gives me the direction of my acceleration. And if you look at that compared with this, you see that is towards the center of the circle. So A, acceleration acts towards center of circle. Now something that acts towards the center is called centripetal. So this is our centripetal acceleration. So there's only one more thing to do then, is if we have a centripetal acceleration, then we need to know how to work that out. And you'll derive this equation in year 13 when you do oscillations with your other teacher. But there is our second equation here. Well, one of many, which is key. So acceleration is equal to omega squared, omega being 2 pi over t, times r. And we know to find the centripetal force, therefore, how much force is acting towards the center of the circle, which is deriving this acceleration. We multiply throughout by m, because ma is from F equals ma. So we can now say that force, centripetal force, m omega squared r. So remember, forces cause accelerations. Okay, there must be a force in play for there to be an acceleration. Forces cause these to happen. So this centripetal force is acting towards the center of the circle, as given by this diagram here, and causes this acceleration towards the circle. That's the center. But because the body is moving already with a velocity, the combination of a velocity this way and an acceleration at 90 degrees causes it to move in a perfect circle. Now we're familiar with this idea of moving in arcs with our lessons on projectile motion. Remember, in projectile motion you have an object moving this way with a uniform velocity, but at the same time there is an accelerating velocity acting this way, causing there to be an arc. This is normally g, and we use our uniformly accelerated motion equations to work out how far it's gone and so on. Right, that's our intro. So in the next video we'll look at some problems.